much. Thank you for the invitation. It's a pleasure to be part of the week-long festivities for Claire. I couldn't think of a better reason to come to Stockholm. Okay, so the title is Moduli Space of Twisted Sheaves and Applications, and let me go right into the first topic. So I'll start with a brief reminder of the classical theory of moduli spaces of sheaves. So we start with a projective variety over an arbitrary field. You could think of just the projective space, and you want to study the geometry of this variety in terms of its coherent sheaves. Think of line bundles, vector bundles, any kind of sheaves. Typically, so you would put them in a category that would be an abelian category. If you want to be more modern, then you would maybe look at the boundary derived category of coherent sheaves. And what you want to do is, so the goal would be to construct a space, a moduli space, this M, such that every family of sheaves parameterized by some parameter space T is actually the pullback of some universal object, universal sheaf on the product of X and M. So in particular, for each point of M would give you one sheaf on X. So roughly the points in M correspond to all the coherent sheaves you have. It's not quite true because it depends a little bit on the field, because you might also have to parameterize sheaves that live on some bigger field than the original base field. So it's well known there are a couple of problems, but also interesting questions. Typically, unless the variety is just a point, there are too many sheaves for M to have any chance of being even locally a nice geometric object. So that's usually the boundedness problems. Then there are things like non-separatedness, or the Hausdorff is a problem. And even once you have settled on some kind of space M with this property here, then it might still be very difficult to actually describe its geometry. So the theory beyond Picard varieties goes back to André Weil and then Narasimhan Seshadri, but really to Mumford in the early 60s. Who constructed the moduli space of stable bundles and semi-stable bundles on curves. Giesecke and Maruyama then tried to extend this to higher dimensions. The theory became extremely technical and heavy. In the late 80s, early 90s, Simpson then seemingly effortless constructed these moduli spaces in great generality. I learned the theory from the expositions of Le Potier. Adrian Lange, 10 years later, then settled the case of positive characteristic by proving boundedness of semi-stable sheaves. And more recently, only a couple of years ago, a new approach was suggested by Heilpern, Leistner, and Heinloth using theta stability. So for all of you who've seen this before, you know there are certain things that go into it. So you have to define what stable means with respect to some ample line bundle. You have to fix Chern-Clausen and Hilbert polynomials. But let me not go into this. So the upshot is we do have these moduli spaces. Let's look at the easiest case. That would be the Picard variety. That's a very classical theory. So for instance, we could look at a smooth projective curve, and then we know the line bundles on the curve, they form a group. That's the Picard group. And via co-cycle description, we also know how to identify it with the first cohomology of the sheaf of invertible functions. However, when you want to construct a moduli space, the Picard group itself will only be a subset of the points of the Picard variety. So in this case, that's our moduli space of line bundles, the Picard variety. And the Picard group is a set of points in this Picard variety. The Picard variety itself decomposes into a countable number of connected components parameterized by the degree, and then each of these pic Ds is really a projective variety over the original field you worked. If the field is the field of complex numbers, then you can be much more concrete. Then the zero component, pick 0c of the Picard group itself, can be described as this quotient via the exponential sequence. And then it can really be identified with the closed points of the Picard variety, pick 0d. All the other components are also isomorphic to pick 0, but in a non-canonical way. And it's actually much better to think of them as torsors for pick 0 via the product map. This roughly means that pick 0, this group variety, acts on all the other components by tensor product. For a general field, the situation is a little bit more complicated. We still have the zero component, which is an abelian variety. In particular, there's an origin, so there's really a rational point on this. And the other components are still torsors for pick 0, but they are usually not isomorphic to it, simply because this is an abelian variety, so this always has a rational point, k rational point, and this might not have any point at all. You naively would think that maybe k rational points, so here's k, these are points whose coordinates are really in the ground field k, correspond to line bundles on the curve C itself. It's not quite true. There's an obstruction which lives in the Brouwer group of the field k, and I'll talk more about the Brouwer group of a field and also of schemes a little later, but here it makes an early appearance already. Okay. So now Simpson actually not only constructed Moduli spaces of sheaves, stable sheaves, semi-stable sheaves, he actually looked at sheaves, Moduli spaces of sheaves on what we nowadays would maybe call non-commutative varieties. So he endowed a projective variety with a sheaf of OX algebras. So these algebras are still associative but not commutative. And then he had a couple of conditions, technical conditions, which I didn't put down. So here are the examples he had in mind. He looked at the sheaf of differential operators and also at the sheaf of symmetric co-differentials. One gave then rise to the Moduli space of flat bundles, and the other one to the Moduli space of Higgs bundles. But you could also look at a sheaf like this, which is just the endomorphism sheaf of a locally free sheaf, so of a vector bundle. Of course, the endomorphism of anything is a ring, and that becomes an algebra. It becomes actually an OX algebra because OX acts on every sheaf by multiplication. Slightly more generally, you could look at Atsumaya algebra. So what is an Atsumaya algebra? An Atsumaya algebra, so it's an OX algebra, so a sheaf of OX algebras, looks eta locally or analytically locally like the thing we had before here. So eta locally, it looks like the endomorphism of something locally free, but globally, it is just an algebra which might not be of this form. Okay, to be very concrete, let me show you an example of an Atsumaya algebra. So you could start with two line bundles on your variety. So think of a curve. Both two torsion in the sense that the square of both is the trivial line bundle. Okay. So then you can write down this sheaf here, and you can endow it with the structure of an OX algebra by saying how these elements in L, M, and the tensor product multiply with each other. So L squared via this isomorphism you declare to be 1, and M squared the same, and the product of LM commutes up to this sign. And then you can prove that locally it really looks like a matrix algebra and becomes an Atsumaya algebra. You could think of this slightly more geometrically by saying, well, a torsion line bundle corresponds to an eta cover, and then you can write down this Atsumaya algebra as this sum, and the minus sign here becomes actually the Galois involution of the covering. So in other words, what we did here was, so we can generalize this now. Instead of looking at two torsion bundles, we look at n torsion bundles, and then to any pair of n torsion bundles, we'll write down this sum. So this is the analog of this thing here, and we endow it with a multiplication by this rule, where the theta is a root of unity. And in a way, this gives you a map from this first cohomology, which you can identify with a set of line bundles with n torsion with a trivialization of this nth power to the set of Atsumaya algebras on your variety X. Right, that works the same. That works the same way. Here I add something that will become maybe important later. What happens if instead of an isomorphism here you just take an inclusion? Then you can still use the same rule to define an algebra structure, but that would not be an Atsumaya algebra on the variety X. So locally, it's not a matrix algebra. Okay. So now, suppose you're given your non-commutative variety, a projective variety with a sheaf of OX algebras, then you can, as before, look at the abelian category of coherent sheaves that are also have a structure of a module. And then Simpson, at least in characteristic 0, constructed the locally projective moduli space of semi-stable coherent AX modules. So that works the same way as before. Sometimes somehow the degree of generality in which Simpson actually worked in his paper got forgotten a little bit. So people only remember these two special cases, Higgs bundle moduli space and moduli space of flat bundles. But you can also imply it in particular to an Atsumaya algebra. Okay, locally again, like an endomorphism of a vector bundle, which is much smaller than the algebra he looked at, which like the sheaf of differential operators. So if you're given an Atsumaya algebra, you could first ask, is it maybe globally the endomorphism of a locally free sheaf? Because in this case, there's an argument to show that this category is actually nothing but is equivalent to the category of coherent sheaves on X, and then all these moduli spaces you get are just the moduli spaces you had constructed before. And typically there's an obstruction you can construct, so you can try somehow to reconstruct this E, and you find there's a co-cycle that comes up, which in the end, so this alpha here, which in the end gives you a cohomology class in this cohomology group. And if it's not 0, then your Atsumaya algebra was not trivial in the sense that it was not the endomorphism of a vector bundle. But even if the obstruction is not trivial, you can still use this information to think of this category of A modules, so abelian category of A modules, as twisted sheaves. And so these sheaves here look locally like ordinary sheaves or bundles, but when you glue them, it's not the usual gluing condition you have, but it's twisted by this cycle. In this talk, I will mainly think about the abelian category of A modules, but there's this equivalent point of view where you talk about twisted sheaves. It has a lot of more indices, that's why for a talk is less convenient. And sometimes some of the geometric intuition comes from here, and then you translate this into something for modules over Atsumaya algebra. In this language, for Atsumaya algebras, these moduli spaces of Simpson were constructed once again by Lieblich, Yoshioka, Hoffmann, Stuhler in various degrees of generality. But they are really just special cases of Simpson's moduli spaces. There are a couple of open questions in characteristic, positive characteristic. Sometimes if the algebra is small enough, you can use Lange's result to actually get boundedness in positive characteristic. Okay, let's look at the easiest case. So I come back to a curve. Before I used the moduli space of line bundles on a curve. That was the Picard variety. Now I'm looking at a curve with an Atsumaya algebra. So there's my curve, and I have an Atsumaya algebra. And this is like the smallest, the easiest moduli space is the moduli space of locally free A modules of minimal rank. So if you think back of a curve, and you just look at the case where the Atsumaya algebra is the structure sheaf, then we were just looking at sheaves or bundles on the curve, and then the minimal rank would be 1. In general, the minimal rank would be this number for some reason, and we look at the moduli space of locally free sheaves of those. There's no stability condition, and this, according to Simpson, is locally a projective variety. Let's look at the case of the complex numbers. So, for instance, or more generally, algebraically closed field. Then it turns out that the Picard, this twisted Picard variety, so twisted by the Atsumaya algebra A, is in fact just isomorphic to the original Picard variety. Not canonically though, but still. We don't get any new spaces. The situation changes if you allow a very general field. Then what we still have is that the twisted Picard variety is a torso over the Picard scheme of the curve, but it's generally not isomorphic. For later, I remark here, very similar to the case of the various components of the Picard variety on the curve before, you can argue that if they really exist a locally free sheaf of this form, so if this group or this set is non-empty, then these two spaces are isomorphic, and then the Brouwer class, which I'll talk about in a minute, of the Atsumaya algebra will be trivial. Okay. So there is this point when you work with an algebraically closed field that you really think of the points of the twisted Picard variety as actually sheaves on C, which are also A modules. If your field is not algebraically closed, that's not quite true, because this thing also parameterizes sheaves that live on the curve C after I pass to some bigger field, for instance, to the algebraic closure. So that's why there's this difference. But it's really very much like the case of the components pic D of a curve over non-algebraically closed field. Okay. So that's the easiest moduli space of twisted sheaves, and in fact, so the twisted Picard variety, and in fact, that's the only one I will really need in this talk. Okay, so now I want to spend 2 slides on the notion of the Brouwer group of the algebraic notion. So that's a Brouwer group of a field. This goes back. So your field could be now anything. It could be the function field of your variety, or it could be R. It could be a number field. Really everything. So this theory goes back to people like Brouwer, Hasse, Noether, and then Albert, and then later Witt and many others. And I can recommend this book by Gilles and Samueli, where the whole theory is really explained in great detail. To motivate this, you could start with the cohomology. We know that for any field K, by Hilbert 90, the first cohomology with coefficients in the multiplicative group is 0. For a geometer, this essentially means there are no non-trivial line bundles on spec K. And then you could wonder if H1 if there's a theorem like this for H1, what about H2? And you can approach this by a completely algebraic construction, which should remind you of the things we've seen already. So the Brouwer group of a field K is defined as the set of central simple algebras over the field K. So a central simple algebra is essentially is just an Atsumaya algebra over spec K. That means after base change to a bigger field, this central simple algebra becomes a matrix algebra. And then there's a certain equivalence relation, that's Morita equivalence. Or you could think of this as the set of division algebras over the field K up to isomorphism. Okay? And then the equivalence here is just the equivalence given by a matrix algebra over division algebra being equivalent to D. So then the theorem is this can indeed be identified with the second cohomology. So this is the algebraic description of the second cohomology with coefficients in the multiplicative group. So there are certain natural things you can do. For instance, if you base change, then so if you go from small k to capital K, then you can get a pullback map that, in terms of simple algebras, is just given by the tensor product. So class alpha on little k gives you class alpha capital K for the bigger field, and that's the definition of the class. This map is usually not injective, but you can say if the field extension is finite, the kernel, which is this relative Brauer group, is in fact a finite group. So sometimes going to a bigger field, you lose information. Indeed, that fits with the Azumaya description, because he said that these are classes that after base change become trivial. So this better has a kernel in general. And then there's a classical theorem that describes the Brauer group, this relative Brauer group as a second cohomology for the smaller Galois group, at least in the case of cyclic Galois groups, as this quotient where n is the norm for the field extension. And then the big highlight of the early days of Brauer groups is this theorem by Albert Brauer-Hasse-Noether, this paper from 1932, which essentially describes all Azumaya algebras, at least for number field, at least under some assumptions on the number field, by a construction that looks similar to the one I gave you for line bundles. So you take two classes, 2 units in your field, and you write down a big vector space like this, with this multiplication, where this is again the root of unity, and these are the rules. And if you identify the units up to nth power with the first cohomology with values in mu_n, then this is the theorem that this map is a surjective map. So every Brauer class of order n on the number field k is obtained via this construction. This is like the holy grail of Brauer theory for number fields. Okay. So let me take the opportunity to talk a little bit about some basic invariants for these Brauer groups and Brauer classes. First of all, I said already that any Brauer class can be split by an extension. So indeed, essentially by definition of a central simple algebra, for every Brauer class alpha, there exists an extension, field extension, so that the pullback becomes trivial. Classically, in the theory, you would construct these field extensions as subfields of the division algebra, representing the Brauer class. And then there are two in numerical invariants. One has actually 3 names. It's either called the period, the exponent, or the order, and it's really just the order of the class alpha as an element in the Brauer group. Okay, so that's the easiest invariant. Then there's the index, which is more complicated to define, but also algebraically more meaningful. Here's one definition, so they can define the index as the smallest, as the degree of the smallest extension that trivialize the alpha. In terms of algebras, that means it's the minimal degree of a field extension that turns your algebra into a matrix algebra over the field capital K. And then there's a relation between the period and the index, which is expressed by saying that the period always divides the index, and in fact the 2 numbers have the same prime factors, or in other words, the index divides some power of the period. So these things here together, these 2 divisibility conditions, just say period and index have the same prime factors. Okay, and in fact, this power n is 1 for number fields. So the order of the Brauer class also tells you the minimal dimension of central simple algebra representing this class. But very early on, already in work of Witt and then Amitsur and then Roquette, but more recently also by Clark and Saltman, people got interested in splitting Brauer classes not by finite extensions as in the classical theory, but by fields of positive transcendence degree. So that makes it more geometric, as we will see. What exactly you want to do with it afterwards is not so clear, but it's certainly at first an interesting question whether you can split a Brauer class by certain natural transcendental extensions. Okay. So now I come to back to geometry. After this, the notion of Brouwer groups for fields was extended to rings. Grothendieck in the early days, in the early 60s, then generalized it further to the notion of the Brouwer group of schemes. So there were 2 talks in the Bourbaki seminar in 64 and 65, I believe, and then he added a 3rd article, and all 3 together were then published in these exposés sur la cohomologie. So this is Brouwer 1, 2, 3, and again a recommendation. This is a fantastic book by Kulutelen and Skorobogatov about the geometry of the Brouwer group for schemes. Again, to motivate this, Grothendieck starts with the cohomological description of the Picard group. So, for instance, we could start with the projective variety over K. Of course, he works with any scheme, and then look at the group of line bundles, which via check cohomology, via co-cycle description, you identify with H1 of the sheaf of invertible functions. And then you can also represent this in terms of eta cohomology, where you look at eta cohomology with values in the multiplicative group. And once you have this description, it's natural to wonder how you can describe the second cohomology with values in the multiplicative group. Now it's really GM, so it's eta cohomology and not H1, AH2 with values in OX, so not Zariski topology. And Grothendieck suggested that there should be a description similar to the case of fields, and which was then later proved first by Gabber and then reproved by de Jong, eventually showing that the second cohomology, or at least its torsion part, which usually is just everything, is the Brouwer group, and the Brouwer group Grothendieck defined as the sheaf, as the set of Atsumai algebras modulo some equivalence relation. So again, Atsumai algebras, that means it's an OX algebra, a sheaf of OX algebras, which locally in the étale topology look like the endomorphism of a locally free sheaf. And Morita equivalence is generated by saying in Atsumai algebra, you want this to be equivalent to the Atsumai algebra tensor, the endomorphisms of a locally free sheaf. And that generates an equivalence relation, and then you define your Brouwer group. It is in fact a notion that can be linked to the Brouwer group of a field via the function field. So at least if X is not too singular, the Brouwer group of your variety sits as a subgroup of the Brouwer group of the function field. So you might have a Brouwer group, you might have a variety where the Brouwer group is not very interesting, could be trivial, but the Brouwer group of the function field is usually extremely big. So at least if the dimension is at least 2, so this is a huge group, and your geometric Brouwer group sits as a subgroup in there. Okay, to give you an idea why the Brouwer group of the function field could be much bigger, let me come back to this construction we had in the beginning, where I took 2 line bundles of both torsion line bundles, 2 torsion line bundles, and then I wrote down for you this algebra and provided it with a multiplication, and that does define an Atsumai algebra, and in particular gives you class in this Brouwer group. Okay, so that would be an element in the Brouwer group. Whether it's the trivial element or not, that's completely undecided at this point, but at least gives you an element. Now you could do the same thing with a slightly more general assumption, which I mentioned before, where you only assume that the squares of these 2 line bundles sit in OX. You can still give this an algebra structure. This would not define Atsumai algebra in general, but it does define an Atsumai algebra over the open set where these are isomorphisms. These are isomorphisms. Then it's an Atsumai algebra, and so gives you an element in this Brouwer group of this open subset. And you see now you can go over all these open subsets and you get more and more elements in the Brouwer group of the function field, and that kind of indicates that the Brouwer group of the function field should be typically extremely large. Okay. There's one quick slide where I want to link the Brouwer group to Hodge theory so that you can see, I mean, I alluded to this already for the Picard group, that you can see somehow that they have to do with Hodge structures of weight 1 and 2. So let me say again, I did this for curves in the beginning, that peak 0 for a smooth projective variety of C over C can be identified via the exponential sequence with an abelian variety. So first of all, complex torus, and then you use Riemann-Hilbert bilinear relations to give this the structure of an abelian variety. You can do something similar with the second cohomology. Now you take the second cohomology with values in O, and divide out. Now we're using classical topology when I write singular cohomology, divide out by this thing. That has a completely different structure. It looks similar. So here's a vector space, here's a lattice, but the way this lattice, or the image of this lattice sits in here, is not as nice as for a complex torus. So this quotient, you can form this, but that's a wild thing. Typically it's not Hausdorff. And you could call the whole thing the analytic Brauer group. We don't have a scheme theoretic definition of this object, as just a cohomological definition. If I now go to the torsion parts, then we can write down the torsion part of the Picard group, and we see this is a group of this form. And something similar happens here on the other side. The torsion part now has a similar structure. It's a divisible group, and this is roughly the Brauer group of your variety, up to torsion in H3. So the analogy is really not between the Brauer group and the Picard group. The analogy is between the Brauer group and the torsion of the Picard group. Okay, and maybe I should have said this here. By the way, this description here, so B2 is the second Bendy number, rho is the Picard number, and that gives you this result I mentioned before, that the Brauer group of a complex curve is always trivial. So you see, in this sense, Picard groups are linked to weight 1-odd structures, and Brauer groups are linked to weight 2-odd structures. There's also another similarity. Both the torsion in the Picard group and the Brauer group, they are trivialized by finite covers. So, you know, for torsion line bundles, you always find this finite eta cover that trivializes it. So if you pull it back, then it becomes a trivial line bundle. And similar here, classes in the analytic Brauer group that trivializes under finite morphism actually are contained in the Brauer group. And this is the full description. So there's this analogy between the two settings. So the geometric version of Albert, Brauer, Hasse, and Noether would be a map of this type. So these are line bundles, torsion line bundles on X, and you do a construction like we had the one we had before. Remember, two torsion line bundles. I wrote down an Atsumai algebra, and that gives you class in the Brauer group, which is n torsion. But typically, of course, this map has no chance of being surjective. For number fields, this was a surjection, but the topology of the variety prevents it. For instance, I mean, there could be no H1 here, and the Brauer group could still be non-trivial. Okay, so now in the algebraic setting, I then pass to the question of splitting Brauer classes by field extensions. In order to do this here and to give it a more geometric touch, it's useful to talk about another description of the Brauer group in terms of Brauer-Severi varieties. So Brauer-Severi variety is something that looks like locally like X times a projective space, and locally again means in the étale topology or in the analytic topology. And then there's a certain equivalence relation by which you have to divide out, which is more difficult to explain for Brauer-Severi varieties. And what is nice about this presentation of the Brauer group is that you can describe the subgroup that's generated by the class of Brauer-Severi variety. So you start with the Brauer-Severi variety over X. You look at its class as an element in the Brauer group. That's a subgroup. It generates a subgroup of the Brauer group, and it is exactly the kernel of the pullback map to the Brauer-Severi variety, which is also the kernel for the pullback map of the function fields. Okay, so now this perspective you can use to do something that's closer in spirit to splitting by finite field extension. Namely, you could take any x tilde that sits in P and that sits generically finite over X. If I now pull back the Brouwer class alpha on X that corresponds to my Brouwer severity, if I first pull it back to P, it's already trivial. If I then restrict it to X tilde, it stays trivial. Okay? So that means for every X, I find a generically finite scheme X tilde dominating X such that the pullback is trivial. Okay? So that's the geometric version of trivializing Brouwer classes. Here's another thing you could do. Instead of cutting down to something that's generically finite, you could cut down to something that looks like a curve over C. So it would be a curve, generically smooth curve over X. And the same argument applies. So you can pull back a Brouwer class. So for every Brouwer class on X, you find a curve relative over C such that the pullback is trivial. Okay? These two constructions are very nice, but they have an obvious drawback, namely that you cannot control the degree of this thing. For simple reasons, the period of alpha, so the order of the Brouwer class, divides the degree of this extension. So these finite coverings you're using here get completely out of control. And for curves, you can always fix the dimension, relative dimension, that's a relative curve, but here it's the genus that gets out of control. So the genus grows with the order of the Brouwer class. There is, however, one loophole here, namely for the case that the genus is 1. Okay? Then all it says is that the period divides 0, which is always true. And so Clark, Saltman, but it goes back much further, then ask, can I maybe, for every class, in the Brouwer group of a scheme of variety, find a curve that will depend on the alpha? So by a curve now I mean a curve that's relative over X. So that's a scheme where the generic fiber is a curve. The fiber should be a curve of genus 1, such that the pullback of alpha is trivial. Okay, so that somehow that would be allowed by this restriction. In order to gain some leg room, instead of asking for genus 1 curves, you could ask for abelian varieties, or more generally for abelian torsors. So an abelian torsor is something that looks like a torsor over an abelian scheme over X. And again, the question is, can you find one for each Brouwer class that trivializes the Brouwer class? No, it will be trivial on the whole thing. So it will be, because the Brouwer group of this thing injects into the Brouwer group of the function field. So once you have it on the generic point, you also have it on the whole thing. So there are some results that show there is something that you can do. So there are early results in a PhD thesis by Swedish, but then it was taken up by De Jong and Ho again, published in 2012, and then also Anjo and Auel, who prove that this is true, at least for Brouwer class of small order. So there always exists the genus 1 curve that splits any given Brouwer class. It's some of the approach they took. I don't think this has any chance of being, so you can be skeptical about this approach working for arbitrary Brouwer classes. So you have to invent something else. And then concerning the second question, there's one paper by Ho and Lieblich from 2021, which proves, in fact, there is an abelian torsor for every Brouwer class that trivializes it. And but the dimension of this abelian torsor goes up very much with the period or the index of the Brouwer class. Okay, so last year then we managed with Dominique Mattei to improve this result by Ho and Lieblich, and we could prove that the following. So if there always exists an abelian scheme over X, such that for every Brouwer class I find an A torso for this abelian scheme that trivializes the Brouwer class. Okay, so when I say a generic abelian scheme, that means that's a variety A over X over an open set. This really behaves like an abelian scheme. So the generic fiber is an abelian variety, and here the same thing. That's an abelian. That's a torso for this abelian scheme over some open subset, and the pullback of the Brouwer class is then trivial. The difference here in comparison to the result by Ho and Lieblich is that all these abelian torsors we constructed have this dimension, of course, of the abelian scheme, which is independent of the Brouwer class itself. So in particular, the dimension does not depend on the Brouwer class. It only depends on the global geometry of the variety. And roughly, it's linked to the genus of a covering family of curves on your X. There are, of course, many more classes you could possibly want to split, namely all classes ramified classes, so Brouwer classes over the function field, so Atsumaya algebras that live not over X, but over some open subset, and we have some ideas how to possibly attack those, but that's very much open at this point. Okay, maybe 2 minutes for the proof, just quickly, so that you can see how the Moduli spaces come in. I start with my X, then I construct a family of curves dominating the X, so that I get actually, that I don't change the function field here. And then I look at the Moduli space of twisted sheaves on X that actually live on the curves in this family. So here A is representing a given Brouwer class. And if I look at the Moduli space and I look at the product with C projected back to this family of curves, which is birational to X, then I view this as a variety over X. And for a very general point, it is the twisted Picard variety of the curve, the unique curve in my family of curves that passes through the point. And this I can view as a torso over the untwisted Picard, and that's my A in the theorem. So now there's a little bit of tweaking you have to do in order to make this Moduli space a fine Moduli space, so that there exists a universal sheaf, that's a universal twisted Poincaré. This sheaf then is, by definition, there's a Moduli space of twisted sheaves on here, so that's a module over this pullback of the Atsumaya algebra, and since it's supposed to be the analog of a Poincaré line bundle, it has minimal rank. But whenever you have something of minimal rank, then the Brouwer class, which is the pullback of the Atsumaya algebra, has to be trivial, and that's the proof. So it's really not very difficult once you've set up the twisted Picard variety. There's a related conjecture, that's the so-called period index conjecture. It's not quite clear somehow how to link these two questions really, but the general conjecture is due to Collier-Thélaine, that says if you have a variety over an algebraically closed field and you give yourself any Brouwer class, even over the generic point, then the index, we said the index always divides some power of alpha, but this exponent probably might depend on the Brouwer class. And Collier-Thélain's expectation is that this is a uniform exponent, which is given by the dimension of X. This fits with results we know. For instance, dimension X of curves, the Brouwer group is trivial, so this exponent could be chosen 0. For dimension 2, that's actually a theorem of de Jong, at least in characteristic 0, and then in positive characteristic, it was proved by Starr and de Jong, and also Lieblich. And just 2 weeks ago, there was a paper by Hotchkiss in Paris proving one of the few very non-trivial cases, and that's abelian threefolds. De Jong and Perry, 2 years ago, they posted a weaker version actually of the conjecture that is essentially the same conjecture, now only for geometric, so unramified Brouwer classes, and the exponent is not as explicit. And even this is a complicated, difficult question. And they managed to prove this under the assumption that one of the big conjectures, the standard Lefschetz conjectures, in degree 2 holds true. And the second theorem in this paper with Mattei last year, we proved that this is actually always true. There exists this uniform bound for the exponent without assuming any of the big standard conjectures. And moreover, this exponent is again bounded by the geometry of curves covering your surface. So the proof uses the construction of the other proof. Maybe the interesting thing is that we use some vector space that comes out of the theta characters, theta bundle, theta polarization of the principal polarization of an abelian, of the Jacobian, and we construct a vector space, which is a modular over this Atsumai algebra, and then that gives a result. Maybe I take 2 minutes, so I skip over this. 2 minutes, yeah, maybe I should say this. Once we put this paper on the archive, Antje and Auel and Lieblich, they showed us an easy argument for this last step in the proof. We've constructed this complicated vector space of global sections of something that could probably be applied also for other types of moduli spaces by just taking pre-image of the origin in this principally polarized abelian varieties. Okay. I want to finish with something on hyperkähler. Just very quickly, maybe I'll just skip over the first half and give you, I'm running out of time, give you this conjecture. So it's more of a speculation. So you could ask yourself, if I have a hyperkähler manifold of dimension 2n, so the dimension of a hyperkähler manifold is always even, and then the question is there something stronger true than predicted by the conjecture of Coullier-Telaine? Does the index maybe always divides the certain power of the period of alpha? So normally in the Coullier-Telaine conjecture there would be a 2n minus 1, and here I wonder whether it's actually n. That certainly fits for K3 surfaces. And there are some results you can prove. So you can actually prove that this is true for Hilbert schemes of K3 surfaces. You can also prove this for Lagrangian fibrations that are of K3n type. I prove, in a way, a version of the Coullier-Telaine conjecture for general Lagrangian fibrations, but where the exponent is not as good as I want. It's not even as good as the one predicted by Coullier-Telaine. And maybe that's a good point to stop. Thank you.